A commercial airplane can weigh 100,000 pounds, sometimes 200,000, sometimes even 300,000 pounds. Metal, fuel, luggage, hundreds of people sitting in rows, and somehow that entire mass rises into the sky and cruises at 35,000 feet with nothing but air beneath it. There is no cable holding it up, no hidden support, no giant balloon, only a shaped piece of metal moving through something you can wave your hand through without resistance. You sit there with a drink in your hand, looking out the window, and between you and the ground there are miles of empty space filled with invisible air. And that air is generating a force equal to the full weight of the airplane every single second. If that force disappears for even an instant, the airplane is no different from a falling stone. So this is not a small curiosity. It is a fundamental question about how the world works. Ask almost anyone how lift is created and you will hear a confident answer. The wing is curved on top and flatter on the bottom. The air over the top travels a longer path, so it must move faster. Faster air means lower pressure above and higher pressure below. Push the wing upward. The story sounds clean, logical, almost inevitable. But that explanation is wrong at its core. And the real reason airplanes fly is more subtle, more rigorous, and far more fascinating than the version most of us were taught. Most people were taught that when air reaches the leading edge of a wing, it splits into two streams, one flowing over the curved top surface and the other flowing along the flatter bottom surface. And because the top surface is longer, the air above must travel a greater distance and therefore must move faster so that both parcels of air meet again at the trailing edge at the same time. This idea is often called equal transit time. And it sounds so reasonable that it rarely gets questioned. The image is simple. Two tiny parcels of air separating politely at the front of the wing and reuniting at the back like two friends who took different paths around a building and agreed to meet at the far corner. It feels symmetrical, elegant, almost inevitable. But there is a fundamental problem at the heart of this story. There's no physical law anywhere in fluid dynamics that says two parcels of air that separate at the leading edge must arrive simultaneously at the trailing edge. No equation derived from Newton, Euler, Navier, Stokes, or Bernoulli demands such behavior. There is no invisible tether connecting the top molecule to the bottom molecule. No elastic band pulling them back together. No telepathic agreement between streams of air. The assumption was simply inserted because it made the explanation easy to tell. If equal transit time were even approximately true, we would expect experimental evidence to support it. But when researchers actually visualize airflow using smoke in a wind tunnel, or track fluid elements in computational simulations that solve the real equations of motion, they see something dramatically different. The air moving over the top of a wing at a positive angle of attack accelerates far more than the equal transit story predicts. The parcel traveling above the wing reaches the trailing edge much sooner than the parcel traveling below. In fact, it is often far downstream by the time the lower parcel finally arrives. They do not reunite. They are not even close. The entire premise collapses under direct observation. The failure does not stop there. The equal transit explanation depends on the idea that the top surface is longer than the bottom surface. So consider a symmetric airfoil, a wing whose cross-section is identical on top and bottom. According to the longer path theory, there is no path length difference. So there should be no speed difference, and therefore no lift. Yet symmetric airfoils generate substantial lift when placed at a positive angle of attack. This is not controversial. It is measured routinely in wind tunnels and used in real aircraft, especially in aerobatic designs. The theory predicts zero lift. Reality produces lift. That is not a small discrepancy. It is a direct contradiction. take it further. Airplanes can fly upside down. Aerobatic pilots invert their aircraft and continue flying steadily by adjusting the angle of attack. When inverted, the curved surface that was once on top now faces downward. If the longer path story were correct, the pressure difference should reverse and push the airplane toward the ground. Instead, the airplane continues flying because lift depends primarily on how the wing deflects airflow, not on a simplistic comparison of geometric path lengths. The equal transit theory predicts the opposite of what actually happens. Now think about a paper airplane, a simple folded sheet with flat surfaces, no carefully sculpted curvature, no obvious longer path above than below. The top and bottom surfaces are essentially the same shape. According to the equal transit argument, there is no reason for the air above to move faster than the air below. Yet paper airplanes glide across classrooms every day. Children perform experiments that contradict the textbook explanation without even realizing it. The world itself refuses to cooperate with the story. So the equal transit time theory fails in multiple independent ways. It assumes a law that does not exist. It predicts velocity differences that are far too small compared to measurement. It cannot account for lift on symmetric airfoils. It cannot explain inverted flight. It cannot explain the behavior of flat plates or paper airplanes. When a theory collapses from every direction like this, the honest conclusion is not that it needs a small adjustment. The honest conclusion is that it is wrong at the foundation. And once that foundation is removed, we are forced to ask a deeper question. If lift is not created because air parcels are racing to meet at the trailing edge, then what physical mechanism is actually responsible for holding hundreds of thousands of pounds in the sky? When people first hear that the equal transit time explanation is wrong, they sometimes jump to the opposite extreme and conclude that Bernoulli must also be wrong, or that physics itself cannot really explain flight. That reaction is understandable, but it is misplaced. The problem was never the laws of physics. The problem was the model that was chosen and the assumptions quietly inserted into it. Bernoulli's equation is a valid and powerful relationship between pressure and velocity in a flowing fluid. If you know the actual velocity distribution around a wing, Bernoulli will correctly give you the pressure distribution. And if you integrate that pressure over the surface, you will obtain the correct lift. The equation is not the criminal. The false assumption about how the velocity is determined is the criminal. Equal transit time was a guess about velocity, not a law derived from the equations. A useful way to see this is to consider another famous myth that sounds mysterious and rebellious against science. You may have heard that according to the laws of physics, a bumblebee should not be able to fly. The story is often told with a smile, as if nature embarrassed the physicists and proved that equations are arrogant. But the real history is far less romantic and far more instructive. In the early 20th century, someone attempted to apply the standard equations for lift on fixed wings to the wings of a bumblebee. They treated the bee as if it were a tiny airplane with rigid, stationary wings. When they plugged in the numbers, the calculated lift was insufficient to support the bee's weight. The conclusion was not that physics was wrong. The conclusion was that the model was wrong. A bumblebee does not fly like a small airplane. Its wings flap, rotate, twist, and generate highly unsteady flow. Each stroke creates complex vortices that remain attached for part of the motion and then shed in patterns that are entirely different from steady. Fixed wing aerodynamics. When you apply the correct equations for unsteady, rotating, flapping wings, the bee flies perfectly well. There is no paradox. There was only a mismatch between the model and the physical situation. It is like calculating the area of a triangle using the formula for a circle and then announcing that triangles are impossible. The mathematics did exactly what you asked it to do. You simply asked the wrong question. The same mistake occurred with the equal transit explanation of lift. Bernoulli's equation was taken seriously, but instead of solving for the real velocity field around a wing, people inserted a convenient story about air parcels meeting at the trailing edge. That story was never derived from the governing equations of fluid flow. It was assumed because it made the explanation simple and visually appealing. Once the wrong velocity field is assumed, the rest of the reasoning, faster flow above, lower pressure above, lift upward, seems airtight. But the airtight feeling comes from internal consistency, not from agreement with reality. If the starting assumption is false, the chain of logic built upon it collapses. This distinction between a law and a model is essential. The laws of fluid dynamics are encoded in the Navier-Stokes equations. These equations account for inertia, pressure gradients, viscosity, and the way fluid elements interact with their neighbors. Bernoulli's equation can be derived as a special case under appropriate conditions. None of these equations require equal transit time. None of them say that two parcels of air must reunite at the trailing edge. The mistake was not in the mathematics, but in the shortcut that bypassed the mathematics. When engineers design real aircraft, they do not rely on the longer path story. They solve approximately but rigorously the governing equations for the flow around a wing. They use wind tunnel data, computational fluid dynamics, and empirical corrections to capture the actual velocity and pressure fields. The lift they predict matches experiment closely enough to carry millions of passengers safely every year. That would not be possible if the underlying physics were wrong. It is possible because the underlying physics is sound and the models used are consistent with those laws. So the lesson is not that flight is mysterious or that physics fails. The lesson is that oversimplified models can mislead when they are mistaken for fundamental principles. Equal transit time was an attractive narrative device, not a derivation. The bee myth and the wing myth share the same structure. Take a formula that applies under certain conditions. Apply it where those conditions are not met. And then blame the formula when the result contradicts reality. Physics does not collapse under scrutiny. Weak explanations do. And once we discard the weak model, we are free to examine what the real equations and real flow patterns are actually doing around a wing in motion. If we strip away every misleading shortcut and start from the most basic physical principle available, we arrive at something far simpler and far more solid. Newton's third law states that for every action there is an equal and opposite reaction. This is not an approximation. It is one of the foundational pillars of mechanics. If a wing is generating lift, it must be exerting a force on the air, and the air must be exerting an equal and opposite force on the wing. The question then becomes direct and concrete. What is the wing doing to the air? You can feel the answer with your own body. Imagine riding in a car at highway speed and extending your hand out the window. If you hold your hand flat, parallel to the ground, you feel mostly drag pushing it backward. The airflow passes over and under your hand with little vertical deflection. Now tilt the leading edge of your hand upward by just a few degrees. Instantly, you feel a strong upward force. Your muscles must resist it to keep your hand steady. What changed is not the shape of your hand, but its angle relative to the oncoming air. By tilting it, you are redirecting the airflow downward. The air that strikes the underside of your hand leaves, moving with a downward component of velocity that it did not have before. According to Newton, if you push air downward, the air pushes you upward with equal magnitude. This downward deflection of airflow behind a wing is called downwash. It is not a metaphor. It is measurable. In wind tunnel experiments, thin streams of smoke show a clear downward bend in the flow after it passes the wing. In flight, large aircraft produce visible disturbances in clouds or on the surface of water when flying low, revealing the sheet of air moving downward behind them. The total rate at which momentum is imparted downward to the air must equal the upward force on the airplane. If an aircraft weighs 100,000 pounds, then each second it must be transferring downward momentum to the air at a rate equivalent to that force. There is no escape from conservation of momentum. Lift is the reaction to air being accelerated downward. The concept of angle of attack becomes central in this framework. The angle of attack is the angle between the wing's chord line and the direction of the oncoming airflow. Increase this angle, and the wing deflects more air downward, increasing lift. Decrease it, and less air is deflected, reducing lift. This is why pilots control altitude and climb primarily by adjusting pitch, which changes the angle of attack. It is also why an aircraft can fly inverted. When upside down, the pilot increases the angle of attack relative to the inverted orientation so that the wing still deflects air downward relative to the earth. Lift depends on how the airflow is redirected, not on which side of the wing appears curved to the eye. However, this process has limits. If the angle of attack is increased too much, typically beyond 15 to 20 degrees for many airfoils, the airflow can no longer follow the contour of the upper surface smoothly. The flow separates, creating a turbulent wake and destroying the smooth pressure distribution that contributes to lift. This condition is called a stall. During a stall, lift drops sharply while drag increases dramatically. The wing is still interacting with the air, but not in a controlled, efficient manner. Pilots are trained extensively to recognize and recover from stalls because the loss of lift can be sudden and dangerous. Even in this failure mode, Newton's third law still holds. The difference is that the pattern of airflow changes so that the downward momentum transfer is reduced. The Newtonian picture provides a powerful intuitive anchor. It tells us that lift cannot exist without air being accelerated downward. It explains why changing the angle of attack changes lift. It explains inverted flight and the behavior of flat plates as well as curved airfoils. It grounds the phenomenon in conservation laws that apply universally. Yet while this explanation captures the essential mechanism, it does not tell the whole story. It tells us that air must be deflected downward, but it does not yet explain in detail how the pressure distribution around a wing arranges itself so that most of the lift often comes from the upper surface rather than the lower. To understand that deeper structure of the flow, we must look more closely at what happens in the thin layer of air that clings to the surface of the wing and shapes everything that follows. The Newtonian picture tells us that air must be deflected downward and that the reaction force supports the airplane. But measurements reveal something that at first seems counterintuitive. On a typical wing at cruise conditions, a large portion of the total lift, often the majority, comes not from high pressure pushing upward on the bottom surface, but from low pressure pulling upward on the top surface. This means the detailed structure of the flow above the wing matters enormously. To understand that structure, we must examine a property of fluids that is easy to overlook because we do not feel it directly in daily life. Air is viscous. Not very viscous compared to honey or oil, but not perfectly frictionless either. At a solid surface, the air in contact with that surface has zero velocity relative to it. This is called the no-slip condition. It is not a guess or a convenience. It is a deeply verified empirical fact in fluid dynamics. If the wing is moving through the air, The layer of air molecules touching the metal surface shares the wing's velocity at that exact point. Just a tiny distance away from the surface, the air moves slightly differently. A millimeter away, the velocity has increased. A few millimeters farther, it increases again. Eventually, at some small but finite distance from the surface, the air reaches the full free stream velocity of the oncoming flow. The thin region, where the velocity transitions smoothly from zero at the surface to nearly full speed outside, is called the boundary layer. Although it may be only a few millimeters thick on an aircraft wing at cruising speed, this layer determines the fate of the entire flow pattern. For decades in the 19th century, theorists struggled with the mathematics of fluid motion. On one side, they had inviscid flow theory, which ignored viscosity and was mathematically elegant but produced unrealistic predictions, such as zero drag. On the other side, they had the full Navier-Stokes equations, which included viscosity but were extremely difficult to solve in practical situations. In 1904, a young German physicist named Ludwig Prandtl presented a short paper that changed everything. His insight was deceptively simple. Instead of trying to solve the full viscous equations everywhere, he proposed dividing the flow into two regions. Outside the thin boundary layer, viscosity could be neglected to a good approximation, and the simpler inviscid equations could be used. Inside the boundary layer, viscosity dominated and had to be treated carefully. By solving the simplified equations in each region and matching them at the boundary, he created a framework that captured the essential effects of viscosity without being mathematically impossible. This was the birth of modern aerodynamics. Prandtl's idea showed that even a very small viscosity can produce profound changes in the structure of the flow because its effects are concentrated in a thin but decisive layer. The presence of the boundary layer has several crucial consequences for lift. One of them concerns how the flow leaves the trailing edge of the wing. In an ideal inviscid world, the flow could wrap smoothly around a sharp trailing edge from the lower surface to the upper surface without any penalty. But in the real viscous world, the boundary layer resists such abrupt changes in direction. The air cannot make an infinitely sharp turn around the trailing edge while satisfying the no-slip condition. Instead, the flow adjusts so that it leaves the trailing edge smoothly, a requirement known as the Kutta condition. This condition is not imposed arbitrarily. It emerges because viscous forces within the boundary layer prevent physically unrealistic behavior at sharp edges. When a wing first begins to move through still air, the initial flow pattern does not yet satisfy this smooth departure condition. For a brief moment, the air attempts to wrap around the trailing edge in a way that would violate the constraints imposed by viscosity. The result is the formation and shedding of a starting vortex that drifts downstream. Once that vortex is shed, the flow reorganizes itself into a stable configuration that satisfies the Kutta condition. From that point onward, a steady pattern of velocity and pressure is established around the wing. What appears from a distance as a simple stream of air sliding over metal is, at a closer level, a delicately structured field shaped by the thin boundary layer clinging to the surface. Without that thin layer, the flow would behave in a radically different way, and the mechanism that allows sustained lift to develop would not arise in the same form. Prandtl's breakthrough did more than solve a mathematical difficulty. It revealed that the small and seemingly negligible property of viscosity governs the global behavior of airflow around wings. The boundary layer, though almost invisible and astonishingly thin, dictates how the flow separates, how vortices form, and how pressure distributes itself over the surface, in doing so, it sets the stage for the circulation around the wing that ultimately determines the magnitude of lift. The story of flight, therefore, hinges not only on large-scale deflection of air, but also on microscopic friction at the surface, a subtle interaction that reshapes the entire aerodynamic picture. Once the boundary layer is understood and the role of viscosity at the surface is acknowledged, we can examine what truly organizes the flow around a wing into a lift-producing pattern. When a wing first begins moving through still air, the flow does not immediately settle into a steady configuration. For a brief instant, the air attempts to curl around the sharp trailing edge in a way that would violate the smooth departure required by viscosity. Because the air cannot sustain that sharp turn while satisfying the no-slip condition, a small swirling structure forms at the trailing edge and is shed downstream. This is called the starting vortex. It drifts away behind the wing, carrying a certain amount of rotational motion with it. Here is where a profound principle of fluid dynamics enters the story. In an inviscid region of flow, away from the thin boundary layer, the total circulation within a closed loop of fluid cannot spontaneously change. This idea is captured by Kelvin's circulation theorem. When the starting vortex is shed with rotation in one direction, the fluid as a whole must respond so that an equal and opposite circulation develops elsewhere. That equal and opposite circulation becomes bound to the wing itself. It is not a visible whirlpool spinning like water down a drain. Circulation in this context is a mathematical measure of how the velocity field wraps around the wing. If you trace a closed loop around the airfoil and sum the component of velocity along that loop, the result is no longer zero. There is a net rotational tendency embedded in the flow pattern. This bound circulation reshapes the velocity distribution around the wing. The airflow over the top surface accelerates significantly, while the flow beneath is comparatively slower. Importantly, this acceleration is not the result of air parcels racing to reunite at the trailing edge. It is the consequence of the circulation required by the starting vortex and enforced by the Kutta condition at the trailing edge. The flow must leave the trailing edge smoothly, and that requirement selects a specific value of circulation from among many mathematically possible solutions. In pure inviscid theory, without the Kutta condition, there would be infinitely many possible flow patterns around a wing, each with a different circulation and therefore a different lift, viscosity, acting through the boundary layer and the smooth departure condition, chooses the physically realized one. Once the actual velocity field around the wing is established, Bernoulli's equation can be applied correctly. Where the flow speed is higher, the static pressure is lower. Over the top surface, the accelerated flow associated with the bound circulation produces a region of low pressure. Beneath the wing, the pressure is relatively higher. Integrating this pressure distribution over the entire surface of the wing yields a net upward force. That force is the lift. The downward deflection of air, described earlier by Newton's third law, and the pressure distribution described by Bernoulli are not competing explanations. They are two consistent descriptions of the same physical reality viewed from different angles. The elegance of this mechanism is captured in the Kutta-Joukowski theorem. This result states that the lift per unit span of a two-dimensional wing is equal to the fluid density multiplied by the free stream velocity and multiplied by the circulation around the wing. Three quantities, density, velocity, and circulation, determine the lift. The specific curvature of the airfoil, whether symmetric or cambered, thick or thin, influences lift only through how it shapes the circulation that develops under the Kutta condition. As long as a non-zero circulation is established, lift follows directly. The chain of events is therefore coherent and physically grounded. The wing begins moving. Viscosity within the boundary layer enforces smooth flow at the trailing edge. A starting vortex is shed. Kelvin's theorem requires an equal and opposite bound circulation around the wing. That circulation modifies the velocity field, producing low pressure above and higher pressure below. The integrated pressure difference generates lift, and the associated downward momentum imparted to the air satisfies Newton's third law. Nothing in this sequence relies on imaginary air parcels reuniting at the trailing edge. It relies instead on conservation laws, viscous boundary conditions, and a circulation selected by real physical constraints. Long before boundary layers and circulation were understood, mathematicians confronted a result that seemed to undermine the very possibility of aerodynamic forces. In the 18th century, Jean-Laurent d'Alembert analyzed the motion of a solid body moving at constant speed through an ideal fluid, one that was perfectly incompressible and completely without viscosity. Using the best mathematics available at the time, he calculated the pressure distribution around the body and integrated the forces. The answer he obtained was astonishing. The net force was zero, no drag, no lift, no resistance of any kind. The fluid parted smoothly in front of the body and rejoined symmetrically behind it. And every push from one side was canceled by an equal push from the other. According to this elegant inviscid theory, a body moving steadily through a perfect fluid would feel nothing at all. This became known as D'Alembert's paradox, because it directly contradicted everyday experience. Ships encounter resistance in water. Arrows slow down in flight. A person leaning into a strong wind feels a definite force, yet the mathematics of the idealized model predicted none of it. The disturbing part of the paradox was not merely that the model was wrong, but that real fluids, such as air, have very low viscosity. Air seems almost frictionless to human senses. It was natural to expect that a nearly inviscid fluid would behave almost like the perfectly inviscid ideal. Instead, the ideal theory produced a result that was not approximately correct, but maximally wrong. Zero lift and zero drag are not small errors. They are complete failures. How could such a tiny physical property as viscosity, almost negligible in magnitude, produce such a dramatic change in outcome? This question puzzled scientists for more than a century. The resolution came with the understanding of the boundary layer. Viscosity, however small, cannot be ignored at a solid surface because of the no-slip condition. Even an infinitesimal viscosity creates a thin region near the surface where velocity gradients are large and frictional effects dominate. Within this boundary layer, the flow can separate from the surface, generating asymmetry between the front and rear pressure distributions. That asymmetry destroys the perfect cancellation predicted by inviscid theory. It allows drag to appear. It also permits the establishment of the Kutta condition and the bound circulation required for lift. The crucial insight is that the limit of zero viscosity is not smooth. Mathematicians call this a singular perturbation. The behavior of the equations at exactly zero viscosity is fundamentally different from their behavior at any non-zero viscosity, no matter how small. You cannot approach the inviscid solution gradually and expect it to resemble reality. At the boundary between zero and non-zero viscosity, the structure of the flow changes qualitatively. This leads to an irony at the heart of flight. The very property that produces drag and dissipates energy, the friction between air and surface, is also what makes lift possible. Without viscosity, there would be no boundary layer. Without a boundary layer, there would be no physically enforced Kutta condition. Without that condition, there would be no selected circulation, and therefore no sustained lift. In a perfectly frictionless universe, a wing would glide through air without resistance, but also without any upward force. The airplane would never leave the runway. What seems like an imperfection in the fluid is actually the ingredient that gives rise to rich and useful behavior. Seen in this light, D'Alembert's paradox is not an embarrassment to physics, but a profound lesson. Idealized models can capture certain aspects of reality with stunning clarity, yet they can also miss the mechanisms that matter most. The smooth mathematical perfection of inviscid flow is sterile. It lacks the asymmetry and structure that real, slightly messy fluids possess. Lift emerges, not in spite of viscosity, but because of it. The microscopic friction in a layer only millimeters thick shapes the global flow field around a wing and enables hundreds of thousands of pounds to be supported in the sky. What appears negligible at first glance becomes decisive when examined closely. That is the deeper resolution of the paradox and the hidden role of friction in flight. At this point, a natural question arises. If the simplified explanation was wrong and the real mechanism involves boundary layers, a circulation, and viscous effects, do we truly understand why airplanes fly? Or are we still standing on incomplete ground? The honest answer is that we understand flight extremely well at the physical level, even if some deep mathematical questions remain open. The governing equations of fluid motion, the Navier-Stokes equations, incorporate inertia, pressure, forces, and viscosity. They describe how velocity and pressure evolve throughout a fluid. In practice, we solve these equations numerically using computational fluid dynamics, dividing the flow field into millions or even billions of small cells and calculating how each interacts with its neighbors over tiny increments of time. These simulations, when combined with wind tunnel experiments and flight testing, predict lift, drag, and stability with remarkable accuracy. Modern aircraft are designed using these methods, and their performance matches predictions closely enough to carry millions of passengers safely across the globe every day. That is not guesswork. That is applied physics functioning at an extraordinary level. Yet within the mathematics there remains a subtle frontier. The Navier-Stokes equations in 3 dimensions are nonlinear, meaning the velocity at one point influences and is influenced by velocities nearby in a complex web of interaction. Nonlinear systems can generate turbulence, intricate vortices, and chaotic motion that resist simple analytic solutions. Mathematicians have not yet proved whether smooth solutions to these equations always exist for all time, or whether singularities might form under certain conditions. This question is one of the Millennium Prize problems. It is a profound and difficult issue in pure mathematics. But this unresolved problem does not imply that flight is mysterious or unexplained. It means that while we can compute and measure fluid behavior with great success, we have not completed the most rigorous mathematical proof about every possible behavior of the equations. It is important not to confuse these levels of understanding. We can calculate the lift on a wing through several consistent frameworks. Newton's third law tells us the wing must impart downward momentum to the air. Bernoulli's equation applied to the actual velocity field established by circulation yields the correct pressure distribution. The Kutta-Joukowski theorem relates circulation directly to lift. These are not competing explanations. They are complementary descriptions of the same physical phenomena, just as a piece of music can be described in terms of melody, harmony, or rhythm without contradiction. Lift can be described in terms of momentum transfer, pressure gradients, or circulation without conflict. The physics is coherent across perspectives. The persistence of the equal transit time story illustrates a broader lesson about science education. Simple narratives are easy to teach and easy to remember. They offer closure in a few sentences. The real explanation requires comfort with abstraction, with boundary layers only millimeters thick, shaping global flow patterns, with circulation that is not a visible swirl but a property of a velocity field. When a simplified model is mistaken for fundamental truth, it can endure long after it has been corrected. The danger is not ignorance, but confidence in an elegant but flawed picture. So do airplanes fly because of a mystery? No. They fly because air has viscosity, because boundary layers form, because circulation is selected by the Kutta condition, because pressure differences arise from real velocity fields, and because momentum is transferred downward in accordance with conservation laws. They fly because the universe obeys consistent physical principles that we have uncovered step by step through experiment, mathematics, and engineering. The story is not that nobody knows why airplanes fly. The story is that the real reason is more intricate and more beautiful than the shortcut version most of us were first given. When you look out the window at a wing slicing through the sky, you are witnessing not a paradox, but a triumph of layered understanding, where subtle microscopic effects shape vast macroscopic consequences. That is not a failure of explanation. It is a reminder that the world is deeper than the first answer we are offered.